So hello everyone. I'm Dušan Isailović, an assistant professor from Faculty of Civil Engineering, University of Belgrade, Serbia. And today I'll talk on how we go from open source 3D city models to auditable assessment estimation of timber and concrete in city roofs. So, why focus on roofs? We all know that circular construction needs scalable estimates of material stocks in existing buildings, and roofs here are important because they strongly influence the refurbishment and the replacement cycles. They contain relevant material layers and structural components. And what is convenient here is that they are usually visible in 3D models, semantic roof structures in various levels of details. And they often follow recognizable typological patterns. However, this geometry of roofs in 3D city models isn't straightforwardly ready for use in material quantity assessment. So this research is a part of the European Horizon project CircBoost, and our workflow here uses 3D city models where each building actually is used to extract its elements and multiply the surface, because all the elements are represented by surfaces, and each multiplied surface is extruded to model the solid layers of materials. So we do that for walls, doors and windows, roofs, also for foundation slabs, and also for intermediate slabs between floors. So this logic works for most of the elements, but roofs are an exception, because you can easily model roof cover layers as an extrusions of the roof surface, because geometrically they are that, but for the structure it doesn't work, and situation becomes even more complicated, having in mind the wide variety of possible structure systems, and it's also to be guessed, because we don't know what is inside the or beneath the roof cover. So our proposal is a traceable chain. We use geometry as an input to classify the roof type. Then we measure some metrics, and then we apply rule-based material quantities. So we use Cityjson as a backbone, explicit geometric rules. So they are readable and challengeable. We don't use the end-to-end learning, because when dealing with thousands of buildings on a city scale, what we value mostly, or equally as the end line accuracy, is traceability and robustness of the representation. So we all implemented that in a single dependency-free Python module, where each threshold is a named constant, and basically every intermediate is exported so we can trace everything. So the pipeline goes like this. We extract roof faces, so semantic first, and with some geometric fallback, we merge triangle soup, which we will see, and you might guess what it is, into the clean roof planes. Then we recover ridges and valleys from the shared edges. Okay, this is a mistake. So we extract the metrics and quality assurance parameters. Then we classify roofs, and in the end we just map types and spans into quantities. So how we get from triangle soup to roof planes? Basically, we perform this merging rule where all the faces with normals within 1 degree on one hand, on the other hand, with the centroid within 8 centimeters, that's empirical value, of course, from the candidate plane, we consider as one plane. So this second rule is just to eliminate this parallel but offset planes to just avoid this situation. So usually we have this situation in 3D city models that everything is like all the planes are separated. So we need that to merge. And for the adjacency, we established a deterministic shared edge map where edges shorter than 20 centimeters are ignored, and edge sign against normals of 2 faces are just deciding on the ridge or the valley. So just to be able to perform on a LOD3 model 2, we just activated this tiny plane filter where planes smaller than 2 square meters or 2% of roof area are excluded, but included actually in the QA. Okay, so how the roofs are classified. If the maximum slope of all the roof planes is less than 5 degrees, we classify it as a flat roof. If we have one roof plane with slope larger than 5 degrees, then it's a shed roof. Exactly 2 dominant planes, each larger than 15% of the area, and valleys less than 5%, then it is a gable roof. 3 to 5 dominant planes and valleys less than 10% is a hip roof, and the rest would be classified as a complex, but with a fallback that, of course, this needs to be validated manually. So here are the metrics. So each roof, for each roof, we measure roof's surface area, projection area, with subtracted holes from like windows and chimneys and these kinds of artifacts. Steepest slope of the plane, effective plane count, of course, and the span is calculated because not every footprint is in such a shape that it can be deducted directly. So we basically calculate the horizontal ring. We take the largest ring and the minimum area rectangle, and the shorter side we consider as a span. So we also extract the QA quality assurance parameters such as manifold, non-manifold edges, and tiny plane count and area ratio. And how we get from these types and spans to quantities. So we basically perform this. If more than one class is admissible, then we use this rule of the lightest admissible class, meaning the class with the lowest timber consumption. So for the timber, the volume is calculated as this projection area multiplied by this normative structural class, which is dependent on the type and the span, and also this complexity correction from valley intensity. It is also calculated. So for concrete, it is much more straightforward because it's applied only on flat roofs. So it is basically just a solid slab. Yeah. Our test bed consists of 88 labeled buildings of a Belgrade quarter in 2 levels of detail, so level of detail 2 and 3, and we have 6 BIMs as a validation set for quantities. So here are the results. We have 1.72 0.72 accuracy and macro of 0.54. This is a confusion matrix, and the findings are that best performing class is definitely shed roof with a macro of 0.9. A bit less performing are complex and flat, 0.7, and low performing class is gable with 0.36. So main error patterns are flat versus non-flat ambiguity, and also gable versus complex ambiguity. And we have a problem that hip roofs are underrepresented in the data set. So it is important to point out that using 2 different LODs, using the LOD3 drops the accuracy to 0.56, and the reason for that is the dormers, chimneys, parapets, and such artifacts inflate plane counts, so it derails dominance rules. And we activated this tiny plane filtering, but it happens that it's not enough. So what also can be concluded is that misclassification of the roof type doesn't affect materials equally. So timber is quite robust. It has 2% of the mean relative error, whereas concrete is much more sensitive, but it's actually reasonable because all the pitched roof types are mapped into timber, and only the flat roofs are concrete ones. So the BIM validation showed that estimates land in the right regime. Remaining gaps are typology and the modeling scope. And the highest value improvement would be this much sharper flat, non-flat decision. So to conclude, I presented an open city model, auditable roof material quantities assessment framework, and we didn't use any deep learning or end-to-end learning. Our preference was traceability and robustness and like interpretability of results. So we also consider, of course, the deep learning for some ambiguous cases, and the results show that timber is robust, concrete can be fixed, and we find an LOD operational LOD, and the next steps would be roof instance segmentation, generalizing LOD3 in the stable structural surface, and area weighted flatness instead of maximum slope trigger. This would sharpen the non-flat or non-flat decision for concrete. Thank you very much.
Thank you very much.